Lesson 12, Exothermic and Endothermic Reactions. So let's just do a little review here. What is the difference between a physical change and a chemical change? So let's look back at our Lesson 3 notes here. Physical change is when we alter a substance without changing its composition. But a chemical change is a change that involves one or more substances turning into new substances. So a simple thing we could write here is that the difference between a physical and chemical change is new substances are formed in a chemical change. Substances formed in chemical change. And we have the signs that a chemical change has happened. And one of the big signs is that there is a temperature change. If we see a temperature change, then we know a chemical reaction has happened. And so that's what these type of this concept that we're learning is quantifying, measuring the temperature change, which temperature is a measure of energy. So let's look at a familiar reaction, the combustion of methane. Another word for this is natural gas. So we would see this in a gas stove. So you're going to answer these questions in the video here. What are the starting substances in a chemical reaction called? This is review from a previous lesson. You could look back in lesson 11a. And what are the new substances? Okay, coming back, if you wrote reactants and products, you were correct. Okay, so here is our chemical reaction, the same chemical reaction. Methane is added to oxygen, and carbon dioxide and water are the products. And what happens in chemical reactions, what we've learned recently, is that bonds get broken. So these bonds in methane all have to break. And these double bonds here in oxygen all have to be broken so that new bonds, in this case between carbon and oxygen, double bonds, and between hydrogen and water, single bonds, so that those new bonds can form. So one new concept is when we break bonds, is energy added or released in order to break bonds? So think about if you have two strong magnets that are stuck together. In order to pull them apart, you would have to add energy. You would have to use your muscles to pull them apart. That's an analogy for chemical bonds. Chemical bonds also need energy added in order to break them. So we're going to circle energy is added to break bonds. Then on the other end, so if we are needing to break the bonds here in our reactant molecules, all these bonds, energy will need to be added in the form of heat. Then when the new bonds formed, it's the opposite. Bonds forming release energy. Just like if we were to hold two strong magnets next to each other with opposite poles faced toward each other, we could just let go of them and they would slam together on their own. We wouldn't have to add any energy. And so in order for a reaction to start, we're going to need to add a little bit of energy to break those bonds. So just like in a gas stove, you have to have a spark, right? You have to add in a little bit of heat, either in the form of a spark from your stove or a match, right? Or if you have a camping stove, a match, you'll need to add it in. And that is, in chemistry, what we call activation energy. It's the energy that needs to be added in order to break the bonds in the reactant molecules. So, for example, lighting methane gas with a match. We're adding a little bit of energy in, and then the reaction just kind of explodes on its own. Once we add a little bit of energy in, we don't have to keep adding energy in, and we'll look at why here. So we would call methane gas because the whole reaction releases heat, or and more generally we can say it releases energy. So we're going to say plus energy on the product side of the equation because energy is released. And this is an exothermic reaction. So we're going to look at a little graph here of an exothermic reaction. And this graph, we have energy on this axis. So as we go up the graph, this represents higher energy. And then this axis is the reaction progress. So it's like time. As time goes by, what's happening to the energy? So we're going to draw in our reactants. So in this case, we started with CH4 and oxygen. And they start at a certain energy level down here, and then we have to add energy, right? We have to add energy in the form of our match, our heat. So we could say down here, the energy is added in as the heat from the match, right? That energy is enough to break the bonds between the carbon and the hydrogen. So this bond here, right, break all of these bonds. So then we just have individual atoms. So we could draw these atoms now individually. We have carbon, we'd have 4 hydrogens, and I guess there's 2 oxygens here. So we'd have a total of 4 oxygens. So now they're individual atoms and they're ready to form their new bonds, right, with the new substances to make carbon dioxide and water. And so here's a question in the video. You're going to ask, when these new bonds form to make carbon dioxide and water, when these new bonds form, is energy added or released when those new bonds form? So answer that question in the video. Coming back, if you said that energy was released when the new bonds are formed, you are correct. We have that note up here. Energy is released when bonds form. So then in our graph, we're going to draw the energy of this graph going down because energy is being released. And in fact, in this particular reaction, because it's exothermic, more energy is released than was added. And so we can circle this now. In exothermic reactions, more energy release more energy than they absorb. So let's draw a little arrow here. And we're going to label this arrow total energy released. And then the difference here in the energy that was added and the energy that was released, that is how much heat we're going to get from that reaction to heat our food or heat our water or heat our homes. So this is that little red arrow is the difference in energy. And that difference in energy is the energy that is released by the reaction. So that's why we use hydrocarbons, carbon and hydrogen, for energy. Because when we burn them in oxygen, they release a lot of energy. So natural gas, CH4, wood is also a hydrocarbon. It's a bunch of carbons and a bunch of hydrogens together. Sometimes hydrocarbons are generically written as this, CXHY, meaning there's some number of carbon and some number of hydrogen. Gasoline that we put in our cars is another fossil fuel hydrocarbon. That these bonds in hydrocarbons are high energy bonds. The electrons basically in those bonds are in a high energy state. And then these bonds, those electrons are in a low energy state. And we see that here in our graph, right? If we can draw in now the products. So the products were CO2 and 2 waters, right? They're at a lower state. And because those bonds, the electrons in those bonds are in a lower energy level, the carbon dioxide and water are not useful as fuel. We can't burn carbon dioxide and get heat from it, or burn water and get heat from it. In order to make the reaction go the other way, we'd have to add energy in. Okay, so let's fill out this last part. In an exothermic reaction, reactants store more energy in their bonds than the products. That's what we were just talking about. So these bonds here are storing a lot of energy. And then these bonds, not so much. Okay. So, and then this is a little analogy here. Someone pushing a ball up a hill, activation energy. So once that person gets it to the top of the hill, they are not going to have to add in any more energy. It's just going to roll down by itself. They don't have to keep pushing it. So that's a good analogy for activation energy. The amount of energy you have to add to get the reaction to just start happening on its own. Okay, and we'll do another video for the